So this is Unit 1, Lesson 13 of our calculus class. The unit is called Limits and Continuity. The lesson 13 is called Confirming Continuity over an Interval. What we're going to learn in this lesson is what does it mean for a function to be continuous over an interval of x values, and what we can tell about a function's continuity just based off of its type. So our definition for continuity is a three-part definition. So we need to know that f of c is defined. We know that the limit of as x approaches c of f of x also exists, and we know that 1 and 2 are equal to each other. So the limit as x approaches c of f of x is equal to f of c. This is continuity at a point. That's kind of something we've talked about before. So continuity over an interval is a function. When a function is continuous on an interval, if the function is continuous at each point on the interval. So given some function on an interval from a to b, we have a continuous function from a all the way to b. The informal definition for continuity is you can draw the whole function on the interval without lifting your pencil. All right, so here's some common function types that are generally continuous at every point on their domain. A few that are noteworthy are underlined in red because those are the functions on the list that are such that the domain is not all real numbers. So for a rational function, if you have some function p of x over q of x can't equal 0, or the denominator can't equal 0. And when you're working with your trig functions, tangent, cotangent, secant, and cosecant, those can all be written as a fraction that involves sine or cosine in the denominator. So depending on the fraction, sine or cosine can't equal 0. These aren't all the function types. They're just probably the 6 most common ones that you'll see. One question, can a function be, how do you say that? Are there any functions that are not continuous on their domains? And so here's an example of one that would be not continuous given its domain. So every value from a to b, or from the interval a to b, is defined, including c. However, because c is a whole, and it's we have a dot down here, it's not continuous, but it is still defined. So at the point c, or the limit as x approaches c, is not equal to f of c would be our formal way of saying this is not continuous. So some examples. Describe the intervals on which the function is continuous. So here's one of our cosecant, one of our trig functions. Cosecant is the same thing as 1 over sine. We know that the denominator cannot equal 0, so sine of x can't equal 0, which means anywhere where sine of x equals 0 would be undefined in our function, or not in our domain. Well, we know that sine of negative pi, sine of 0, sine of pi, sine of 2 pi, any multiple of pi would give us a result of 0. So we exclude those values in our interval notation like this. So we say negative pi to 0, in unison with 0 to pi, in unison with pi to 2 pi. And notice we have null brackets, not square brackets, and that implies that pi and 0 and 2 pi and negative pi, all the endpoints of these intervals are not included in the domain. And then dot 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 on the beginning and the end shows that we could keep going in the left direction. After negative pi would be negative 2 pi to negative pi, and so on. And we have those same dot dot dot, or they're actually called ellipses. We have those to the right because we can go more intervals to the right. We can go 2 pi to 3 pi, 3 pi to 4 pi, and so on. So here's interval notation. We can confirm that by the graph of cosecant of x. If x is a multiple of pi, we can find all of our basically asymptotes. See, these are all the points of discontinuity on our cosecant function. And this confirms our graph, not including negative 2 pi, negative pi, 0, pi, 2 pi, and so on. All right, so here's a polynomial one that's rational. We have the intervals on which the function is continuous. So basically the denominator cannot equal 0. This function is very conveniently factored out for us. And so we know that when x equals 2, when x equals 4, and when x equals 6, we have x values that are not defined. And so we can write a notation for our intervals of continuity like this: negative infinity to 2, but not including 2, in unison with 2 to 4, not including 2 or 4, in unison with 4 to 6, also not including 4 or 6, in unison with 6 to infinity, not including 6. So just taking a moment here to remember what this graph looks like. So because I have x minus 2 as a factor on top and bottom of this function, I know that 2, x equals 2, is going to be a hole on my graph. Because that factor is removable in our rational equation, that means we have removable discontinuity on our graph. And x minus 4 and x minus 6 are both factors in our denominator, but they do not appear in the numerator. So that tells me that at x equals 4 and at x equals 6, we have vertical asymptotes. And so we can do a really quick sketch of this graph. We know the behavior at 2, 4, and 6, a hole, and then 2 vertical asymptotes. And we can kind of guess what the rest of it looks like from there. But being able to recognize the difference between a hole and a vertical asymptote in a function like this is going to be a useful skill for us later on down the road. Okay, so we can graph this function and see that at f of 2 it is undefined, and that's because that's our hole on our graph. Where'd you go to? Oh man, I suck at finding these things on the graph. Somewhere over here. But we can see that when we plug in f of 2, it is an undefined question. When we go to 6 and 4, it'll still be undefined because those are our vertical asymptotes. Takeaways for this lesson: knowing the domain of a function can really help us find the intervals of continuity for a function. That's pretty much it. Also, we're going to have to make sure we know how to write interval notation. So if you're rusty on that, make sure you do some brushing up on the homework assignments. And you may have noticed I don't have a beard in this video because I'm way behind on writing these videos. And since I last posted one, I shaved my face. My wife is happy about it. I'll let you decide if that's good or not.